Today I am going to discuss idempotent matrix of order 2. Let's start with some basic concepts. Suppose we have a real matrix of order 2 whose elements are A, B, C, D. Then its trace is given by sum of diagonal elements, that is A plus D. These A and D are called diagonal elements and their sum is called trace of matrix A. The determinant of this matrix is given by product of diagonal elements minus product of non-diagonal elements, that is AD minus BC. If determinant of this matrix is 0, then this matrix is called singular matrix, otherwise non-singular matrix. If diagonal elements of any matrix are 1 and non-diagonal elements are 0, then that matrix is called identity matrix. This is an example of identity matrix. Here diagonal elements are 1 and non-diagonal elements are 0. If all elements of a matrix are 0, then that matrix is called null matrix. This is an example of null matrix. Here all elements are 0. So let's start idempotent matrix. A square matrix A is said to be idempotent if its square is equals to itself, that is A square equals to A. Taking A to left side, we have A square minus A equals to O, where O represents null matrix. Now taking A common, so we have A times A minus I equals to O. The solution of this equation are A equals to O or A equals to I, where O represent the null matrix, I represent the identity matrix. So we can say that the null matrix and identity matrix, they are always idempotent. Now suppose we have a real square matrix whose elements are non-zero, that is A equals to ABCD. Here elements ABCD are non-zero. So its trace is A plus D and determinant is AD minus BC. This matrix will be idempotent if A square equals to A by definition. On substituting the value of A, we have this equation. On simplifying this equation, we get this equation. These two matrices are equal, and we know that if the two matrices are equal, if and only if their corresponding elements are equal, it means this A square plus BC must equals to A, AB plus BD equals to B, CA plus DC equals to C, CB plus D square equals to D. So we have these four equations. From equation 2, we can take B common from the left side. So we have B times A plus D equals to B. B cancel out, we have A plus D equals to 1. Similarly, from the third equation, C is common, we have C times A plus D equals to C. Here also C cancelled out, we have A plus D equals to 1. And this A plus D is nothing but the trace of the matrix. So we have one condition for any real matrix of order 2 whose elements are non-zero. If its trace is 1, it could be an idempotent matrix. For the second condition, adding 1 and 4, we have this equation. On simplifying it, we have A square plus D square plus 2BC equals to A plus D. Now adding a term 2AD and subtracting it. So this one, A square plus D square plus 2AD, this is nothing but the A plus D whole square. And from the last two terms, taking minus 2 common, we have AD minus BC equals to A plus D. But we have proved that A plus D equals to 1. On substituting A plus D equals to 1, we have AD minus BC equals to 0. And this AD minus BC is the determinant of the matrix. So we have two conditions. For any real square matrix of order 2 with non-zero elements, the matrix will be idempotent if the trace of the matrix is unity and determinant of the matrix is 0, means matrix should be singular. For example, we have this matrix A whose elements are 3, 6, minus 1, minus 2. Now find out its trace. Trace means sum of diagonal elements. So 3 plus minus 2, that is 1. And determinant of this matrix is 0. Thus, this matrix A is idempotent matrix. So summary of today's lecture is, any square matrix is said to be idempotent if its square is equals to itself. Null matrices and identity matrices are always idempotent matrices. Any real square matrix of order 2 with non-zero elements will be idempotent if the trace of the matrix is unity and determinant is 0. Thank you very much. For more videos, please subscribe our channel MS Math Solution.